All right, I want to hear you guys' thoughts. So we're going to talk about light today, and light is not only at the center of everything that we can possibly talk about in astronomy, but it's also one of the most poorly understood phenomena in our everyday lives. And I'm going to see what I can do to shed some light on light, but it is kind of at the frontier of our knowledge. There's been a lot of theories tried on over the years as to what the heck light is, and all of them are a little bit short of satisfactory at the end of the day. So we'll see what we can piece together and see what might come next in terms of our ideas about it. But first, what do you guys think from last week? Any thoughts? I want to hear from you guys. Yes.
Like how the moon is formed has always been like up in the air. Because I remember watching like probably like documentaries or something about saying that they crashed into the earth and then like the remaining rocks formed and yeah, I just thought that was interesting. And it reminds me of I don't know if you've heard of the water sphinx erosion hypothesis.
Oh yeah, Robert Schoch, eh?
That's like another thing that made me think about that because I'm like, how much is really like not clear?
Yeah, it's kind of exciting, right? I think we talked about that a little bit last time because you can go off the rails with it really quick and you can be like, oh, we don't know anything. And while there's some grain of truth in that, I think that we have remarkable ability to hold multiple ideas in our head and sort of see which one works best in any situation. But I don't know, how do you handle that? I mean, knowing that the past is a little bit uncertain.
I mean,
Does it bother you?
I don't expect us to fully grasp everything
Yeah.
so fast as they made it seem like. I think growing up, you think things are how they are, and later on you realize it's not. It's just you drive yourself crazy trying to figure it all out.
Yeah.
Yeah, it may all come, it may not in time, but
Yeah, I think in some things we do get a clearer picture over time. And in some things we realize that we were coasting along on mistaken assumptions too. I think it's really exciting and fun personally. But you can go a long ways in life thinking that somebody has the answers before you realize that you're gonna have to think for yourself, which is I don't know, how do the rest of you guys feel about the uncertainty of theory in general? Nolan, yeah.
Yeah, I mean, I guess to follow up, a lot of what I've been researching, I guess, this past weekend and whatnot, one of my roommates is actually native, so I've been having a lot of conversations with him about native culture and as well as like watching YouTube videos of ancient civilizations as well as in Mesoamerica and whatnot, what evolved into what. There's still so much of an unclear picture of what was painted, human origins.
You guys watching the Graham Hancock series on Netflix?
No.
Okay.
No. Mostly just like YouTube stuff.
Anybody following this Graham Hancock thing? No? Because he's an interesting case, actually. So I actually read one of his books when maybe like 15 years ago, and it was a really fun book to read about the potential of missing civilizations underneath who were kind of lost to the oceans, right? Because we talked about climate change, we talked about the glaciation cycles. One of the things maybe I didn't mention, which is worth mentioning, is that the sea levels have risen something like 300 to 400 feet. And the result of that is that like whole bodies of land have been lost. And, one of the most interesting ones to me is this, where Indonesia is, the Indonesian islands. There was a huge landmass there called Sundaland, and it essentially stretched darn near to Australia. And Australia was much bigger also as a result of it. It was still connected to Tasmania. And so the question is, what's down there? Anyways, Graham kind of got famous a little bit off his first book. But he's an interesting case because he came out of the gate and got really pissed off all the archaeologists because he was saying all these really outrageous things, like there's this advanced civilization that archaeologists are hiding from you. But it's funny because in the last few weeks he's done a bunch of interviews and he's really toned it down in a really interesting way, where he's kind of actually, I think, pointing to stuff that's much more plausible and interesting, like that there is a lot of stuff buried under the water, which could tell us a lot about our ancestors, but it's not probably guys with iPhones or anything like that, which is kind of what he's making it sound like. So it's interesting seeing somebody go from being on the conspiratorial side, like the kind of far outside, to really figuring out how to use the language of their peers, and that's an interesting metamorphosis. But anyways, he's got a show on Netflix. It's got some really cool footage of ancient sites and stuff if you're into that kind of thing.
What's it called?
I think his series is called Ancient Apocalypse. Yeah, very. The first season's a little more over the top than this new one. My wife watched a little bit of the first one. We started watching the second one. It's fun. I think he definitely really wants there to be this giant impact after the glaciation that caused the destruction of his lost civilization. There's this event we didn't talk about actually, which is, we see those nice rise and fall of the temperature across time with the glaciations. There's also this one where in the most recent glaciation, it starts to warm up again. And then all of a sudden, for some unknown reason, it gets really cold again for about 1,000 years. It's called the Younger Dryas event. And nobody really knows what caused it. And so Graham and a number of minority position scientists have decided, they've looked at the evidence and they think it was an asteroid impact or an air burst of an asteroid. And he really wants that to be his cause of the disappearance of his lost civilization. So it's very motivated in that sense, but I think it's still entertaining. There is just so much there in the past that's really hard to figure out. When I was in college, the mainstream standard idea, I took an archaeology course just for some credit, and the main story was that the first civilizations in the Americas were, don't quote me on this, but I think around 12,000 years ago. It's called the Clovis culture, and anybody who said anything other than that was kind of treated like a conspiracy theorist or something. And they recently found these, first of all, some, I think, nearly 20,000-year-old footprints up here in Oregon, but also down in White Sands. And this documentary actually covers that. So there's these people, basically, they find their footsteps, and their footsteps are alongside these giant megafauna, right? So mammoths and giant sloths and things like that. So they had to really revise their picture of these things. And there's some other points, too, that suggest people were around in the Americas for much, much longer than we thought.
Fairly recently, there was a body called the Kennewick Man.
Is that the Oregon guy?
No, that was up in Washington.
Okay.
Like a whole skeleton.
Kennewick Man.
Back in 8,000 years, Landbridge from Alaska.
Mm. Yeah, the Landbridge thing is interesting too. That used to be kind of the main story, and I feel like that people are really opening their minds to the idea that, in terms of the speed at which people got to South America, they actually kind of made it down to South America before they started really developing inland, which is weird if it was a Landbridge situation. So people are really starting to think, look at these Polynesian navigators and stuff and say, people probably were on maybe not huge boats, but some sort of boats, and they're probably traveling along the coastline. There's plenty to eat there. It's hard to get lost. You just keep going south. And then, of course, it really is a really interesting point, If that was the case, why don't we see evidence of it? Well, because it's underwater, or, the ocean destroys everything. You guys have been to the Oregon coast, probably. There's nothing left from even 300 years ago on the Oregon coast because they have these tsunamis every once in a while. That destroy even all the big trees. So you're not going to find traces of people there for the most part. The other problem is archaeologists are nerds, right? Scientists are nerds. Being a diver is really athletic. Does anybody dive here? Oh, cool, nice. It's hard, right? It's a serious workout. So finding the Venn diagram overlap of people who are super athletic divers and archaeologists is a vanishingly small population. And so if a lot of the record of what happened during the last glaciation is underwater, as we should expect it should be, that's going to be really hard evidence to dig up.
What's the pay for something like that?
Not good, but you know what? I think the older you get, the less you realize that matters much. It's funny because if you look at who are the rich people, who are the most wealthy people, they're the old people. People around 75 are usually the most wealthy people. But I think they would all trade any of that wealth to be you young people, right? And so when it comes to picking what to do with your life, I would strongly urge you to pick something you enjoy doing rather than trying to make money. Yes?
So that was arguing against the Bering Strait. Is that what we're talking about?
Against the exclusivity of the Bering Strait argument, yeah. I mean, there's also, there's reason to believe too, if you go, it's kind of fun, go on Google Earth and check out the topology of the Pacific Ocean. There's all these would-be islands, right? If you lower the ocean 300, 400 feet, there's a pretty nice chain of islands that would hop you on out here, right? And there's some really interesting and hotly disputed genetic evidence about people of Polynesian Thai ancestry in South America. One of the more convincing ones for me, dating really far back, most people agree that there was some Polynesian contact about 1,000, 1,500 years ago, but chickens. So where do chickens come from? Anybody know? Eggs. Where's the egg come from? No. Chickens come from Thailand, actually, Vietnam and Thailand. They're also all over the Pacific Islands, too. And there's some chicken bones that they found in South America that are dated to more than 20,000 years ago. So it's like, well, where'd those chicken bones come from? Maybe, I mean, it's, again, the past has a tendency to erase so much. Like if you think about the fact that just 10, 15 years ago, people were convinced there was no people in the Americas before 15,000 years ago, or whatever it was. And then it turns out there was just some footprints in the White Sands National Park or something, right? And that's all the evidence that you had for 10,000 years. People were here for 10,000 years doing all the stuff that people do for 10,000 years. And all that they can find right now is a few footprints in one place. So the past really has a tendency to eat things up. And so I think this is relevant to this astronomy course too, because when we start talking about the formation of planets billions of years ago, it's like, holy cow, we are looking at, we are reconstructing like a scene for which we have very, very little direct evidence. And so all these are theories, and we have to be able to hold them in our mind. That's why for your final project, I'll give you guys the handout soon, but what I want you to really do is to imagine some other explanation for the formation of some of these planets. And we're going to talk about different ways that you could do that too. There's a number of different things that are being investigated in the literature that you guys can check out. So I want you guys to get in the habit of thinking about new explanations too that you haven't necessarily heard of before, applying the different types of reasoning that people are going to show us as we get to those bodies later in the course. So this is really important because kind of the worst thing that could happen, and kind of what's happening in a lot of science right now, is people come in, they study under a mentor who knows how to do one thing. You learn how to do that one thing, you move it down the field a little bit further. But there's less and less room for people to really practice real, true innovation and thinking outside the box about what these possibilities could be. And the reality of the situation is that in science and in our understanding of the universe, we generally tend to believe one thing for a long time until all of a sudden we believe something radically new. It's not like our knowledge really is boosted incrementally up to a new understanding. It's usually the old one falls violently and then something else replaces it. So we need more people thinking like that, and you need a chance to practice it because it's a muscle. All right, thoughts? I'm almost through the second pass. I want to make sure. I don't know if these people are in the class. Is Joe here? I think Joe might have dropped the class. How about Manuel? Manuel? No, probably dropped it. Brian, I saw you today. Any thoughts from last week?
I think we kind of rushed on already the tides. I really like the moon. I think it's really sad that it's leaving.
Yeah, not anytime soon.
I grew up on the coast of Oregon, so we just kind of like watch the tide tables. And we're like, yeah, that's like we just treated it as gospel and not thought about it any more than that.
Like with respect to the moon?
Yeah, just like if we wanted to go surfing or diving, we had like each county had their own tide chart. Look at that, and that's just we don't really thought of it anymore.
Interesting.
It's just that.
Its relationship to the moon, yeah. Yeah, it is fascinating. And it's not going away anytime soon, so I wouldn't worry about it. What is it? What did we say? A couple centimeters a year, something like that? And it's about 60 Earth radii away from us right now. So it's pretty far gone to begin with, although it's quite big in the sky still. I don't know that we'll talk too much more about the moon in this course. We will next semester, and we'll talk about a lot of other moons. So there's some really cool moons out there. Have you guys had a chance to look through binoculars and see Jupiter's moons? Highly recommend. Highly recommend. You don't need anything fancy. But if you have like a camera tripod, you can mount it on. It's a lot easier to keep the thing still so your hands don't shake. But it'll really change. I think it'll really change you to see with your own eyes. There's something about seeing pictures of it, especially these high-res kind of pictures that just don't cut it. But seeing it with your own eyes, it really changes your picture of where you are in terms of our own moon too. Thinking about that looking kind of the same way from Jupiter over there. All right. Okay, so I've made it through, I think, the second round of these. Anybody have thoughts from last week? Let's do a couple more. Yes, remind me your name.
Macy.
That's right.
I just thought, following like the moon stuff, I thought it was interesting how the ratio from the Earth and the moon is that it's so large. Like it's abnormally like large compared to the Earth.
Yeah, it's a big moon with the size of its host planet. I think the biggest ratio actually, by a good margin. And what else? Yes.
We touched on it briefly,
Remind me your name. That's right. All right.
and then it was in one of the videos too, but just the fact that like planets aren't definable, and when you do
Mm.
there's always exceptions.
Yeah, it's horrible.
And then they compared it to like a concept like continents. And I just thought that was interesting.
Which are equally difficult. Yeah, chopping things up, the idea of dividing things up is really useful sometimes. Another one that's a nightmare, I'll get to you, don't worry. Another one that's a nightmare is the word species, right? That turns out to be a completely useless word the more you push on it, right? Because you'll hear about, like these different species, like the different hominids, for instance, if we're talking about ancient archaeology or something. But then you find out that humans have Neanderthal DNA, right? Not necessarily from a common ancestor either. The theory is that they were interbreeding. So it's like, well, then those weren't really a different species if they could produce viable offspring, right? And it turns out to be the same with a lot of fish and all sorts of things. So there's these words that we just default to without really thinking about what they mean. I'm going to make the case for you today that light is kind of like that, actually. And it's very ill-defined and poorly understood, even though it's something that we depend on all the time.
Fundamentally.
Yeah, but that's just how you learn, though. It's difficult to, in some sense, because we want to reward people for being right, and so I worry about things like the Nobel Prize. Maybe I've talked about this before, but it's like, there's some of these things. One of the things we're going to talk about today, if we get there, is something about the material basis of the sun itself, which is generating most of the light that we get here on Earth, and our understanding, it's like almost like, who cares how the sun works? Well, the reason you should care is because the technology called fusion, which is supposed to be the next generation of power, we had this huge discussion about environmentalism, let's say, and climate, stuff like that. And we all kind of, I think, agreed nuclear is great, but at the end of the day, turning nuclear loose when you have kind of rogue nations that you don't really trust is problematic. And so fusion is a viable possibility, let's say, and there's been some experimentation. However, all of that fusion science is based on the way that we think the sun works. Now, if the way that we think the sun works is abysmally wrong, it might explain why we don't have fusion reactors in every town right now, too. So it is an important thing, and there are technological ramifications for our misunderstandings sometimes. So we'll play with it. Let's do one more. Who else is here? How about Tyler? You here? Nope. How about Tirza? Nope. How about is Doris here? Hello. Any thoughts from last time?
Definitely super curious about light and where it's headed. Hear about that.
All right. Well, let's get to it then. So I want to give you guys a tiny bit of a picture, but I'm not going to try to bore you with the history too much. Needless to say, we talked about the Greeks a bit, who at least insinuated the idea that the world was made out of little particles of invisible stuff that they called the atom. They didn't have any conception of the atom like we do today, but it was more or less the same idea that there's little chunks of stuff. And they essentially sent that idea all the way down the chain into the Enlightenment thinkers. And so the first people who really started to mess around with what the heck light was were some of these Enlightenment thinkers like René Descartes. I know we've talked about him before. He kind of inherited this idea that maybe light was these little bullets of stuff that was popping off of the atoms, which is still, in some sense, at least schematically, very popular. We'll talk about that in a second. There's this idea of the photon we'll get to. Descartes and later Newton kind of inherited this as well, that these little chunks were composed of these things they called corpuscles. Now, that idea probably would have been fine because, you turn on a flashlight, it goes into, the light seems to travel in a straight line. There's guys, of course, separately working out the idea that light did take time to arrive at its location. So that would have probably held up forever if it had not been for this interference business, which you can see on the surface of a pond, right? And it turns out light does this as well. So if you shine light through these two tiny little slits, it turns out that what you get on the back of the screen is not just these nice two little blobs where the light has passed through the slits, but it seems to produce this spread of interference patterns. So you don't even need slits to do this. You could just take a knife or something sharp and shine a light on it. Lasers work really nicely because it's a very clean source of light. It's all the same wavelength and it's all in phase together. But if you shine a laser on a knife blade, you'll actually get a series of fringes, right? You'll get dark spots and light spots. And what's really weird is that the shadow, the light seems to be reflected into the shadow, and the shadow seems to be reflected into the light part of the laser. So, from basic water mechanics, you can actually do this on the surface of a pond if you throw, if you have waves that are traveling through two little holes in a pond. I should have got you guys a movie of this. But you also get this constructive wave interference where the water's going up, it's going down, and when it's going up and down, it cancels itself out at certain points. And the result is that you get this kind of wave interference pattern. So people started to realize that light did the same thing, and they were like, wait a second, there's no way on Earth we can make little corpuscular bowling ball things do this sort of thing. And that was a real nightmare, and it still is, which is quite interesting. So there's always been two camps in science, and it's worth kind of mentioning these two camps. One is the empiricists, and one is the rationalists. Now, the empiricists, generally speaking, and I would say we live in a very empirical age today, what they do is they say, this is what's going on with this phenomena, let's make some equations to describe how it works in every experiment, and let's move on. And the rationalists say, whoa, 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 we can't just describe how it looks, we need to actually explain what's happening here. And the empiricists say, well, you can't see what's happening, so you can't tell me why those waves are interfering with each other, let alone what's waving in the first place. The rationalists say it doesn't matter, we need to provide hypotheses for what could be waving, right? Because wave is actually a verb, by the way, so you need something to be waving. Now, so they kind of came to a détente somewhere in, like, let's say the 1700s, 1800s, the empiricists and the rationalists. They said, well, there's probably something waving between the one atom that's shooting the light, the atom that's receiving it. We're going to call it the luminiferous ether. We don't really understand how it works or anything like that, but it's fine. It's certainly there because how do you have a wave without an ocean or something, right? It just makes no sense. And that was all well and good all the way up until almost 1900-ish or so, the end of the 19th century, when they made a series of experiments to try to detect this ether, and they failed abysmally to detect it. And so we'll talk a little bit about why they were unable to detect it and what I think might have gone wrong. But needless to say, the rationalists at that point were kind of out of ideas, and the empiricists were like, well, this problem can't be solved. To the point that in the mid-1920s, there was actually a conference that had all of the world's best physicists at it. It was called the Solvay Conference. And I think 75% of the people at that conference went on to win Nobel Prizes in physics. So it was kind of, Einstein, Dirac, all of the big names that everybody has heard about in physics. They all got together and they were discussing this problem, that light seemed to behave like a wave, except for, you could actually quantize it. We'll talk about the quantization in the photon in a second. It also seemed to behave like a particle in that all of the energy from an atomic excitation that gives you light, ended up at one atom at a time. So it had this particle-like ability. In other words, if you do this experiment by providing exactly one quanta's worth of energy to that laser, so it's just one unit of light flying out, you still get this interference pattern. So, how does that work? It's both a particle and a wave. Anyways, these guys at this conference were just like, we can't figure it out, so we're just going to accept that the light is both a wave and a particle at the same time. Let's move on, right? So that's, in some sense, really disturbing because people inherited this idea. And more to the point, there was some interesting work concerning how electricity related to light, electromagnetism, and a very schematic empirical explanation for light came about, which described light as this oscillating electric and magnetic field. Now, what in the world does that actually mean? Well, here's what it means. This is probably the easiest way to understand it. So this is the most simple radio antenna that you can imagine. The way that you make radio waves is you take some sort of antenna and you oscillate the electricity going through it. It's going in one direction, and then it's going in the other direction. The rate at which you oscillate it gives you the frequency of the light that comes out of it. So radio waves are light also, as we'll see. Light is not just visible light, like the ones that's going between our eyes right now. Light is also radio waves, gamma rays, X-rays. It's of various different energies and wavelengths, right? So the simplest way, this is probably the most empirically simple way to understand what light is that atoms are inverting their polarity regularly, and the rate at which they do that is carried forth and propagates outward. Now, outward into what still remains a huge question, right? But the field effects, so what I mean by field effects is that this oscillatory behavior seems to propagate forward. Now, the method by which it does that is still something that is poorly misunderstood. In fact, a lot of physicists today will say stuff like, well, the fields are pervasive and the fields carry the energy of the photons, right? But this is a little bit sidestepping the issue because the field is really just a location of measurement where you measure the strength of that electromagnetic interaction. So in other words, if I took some sort of magnetometer or some sort of electric field measuring device and I stuck it out here away from the radio antenna, I would be able to measure the direction of the electric field, right? So it's really like a sea of measurements. It really doesn't explain how this works exactly, which is troubling. So, this was actually first demonstrated by this guy named Hinrich Herz, and we get the Hertz, which is our frequency measurement in physics, from this guy. He had this rather ingenious little setup where he essentially had an oscillating field in this coil system down here, and he was able to actually send he was able to excite this tiny little ring coil across the room and generate a spark in it. And this is where he realized that this is kind of the first time that people realized that light had some electromagnetic component to it. In other words, he was able to spark electrically something on the other side of the room by generating this radio frequency inside of the first system. Yeah.
Is this somewhat in relation to the practice of switching and taking two copper wires?
That's a weird one. I don't know, and I don't know if that works at all. Okay. Yeah, but maybe. I don't know, like the water dowsing people and stuff like that.
Yeah, so essentially the idea of switching for these copper poles is when you pass over an electromagnetic field, they tend to cross because it's interfering back.
I think they're looking for water. These are how people were trying to find water back in the 1800s or something. Yeah, I've seen these people. It really does look like their hands are moving, but I have no idea. I don't think that it's proven out under scrutiny. But yeah, so in general, it's worth pointing out something here, which is that magnets themselves, and we're going to do magnets next semester, and we'll try to make more sense of this. Magnets are also poorly understood. If you go on the internet and try to read about how a magnet works, the unfortunate result that you're going to have is that you're going to find out that atoms act like little magnets, and that's the end of the explanation for the most part. That is really, really unfortunate. And so we can talk about that next semester. I have some ideas, but needless to say, I think that all of these really confusing phenomena come down to the fact that what we have that's actually observable, that we know a fair amount about, are atoms themselves. We know that the atoms have an outer surface, which is generally called, especially by chemists, the electron, right? Now, the electron's dynamic in nature, so in other words, the outer surface of the atom is always moving in some way, and it moves in a really particular fashion. The other weird thing about the outer surface of the atom is that it doesn't actually stop. So if you look at the distribution of the electron with respect to the nucleus of the atom, what you find is this nice big peak where there's a lot. You can find that electron very often, but sometimes you'll find it at any distance from the atom. So the outer surface of the atom isn't a simple shell, even though the chemists like to call it the electron shell, and you probably learn about it in chemistry, these orbitals, right? Different shells. It's not exactly like an eggshell. There's something else weirder and stranger going on, but what we can seem to say is that the atom does not end at the shell. There's some portion of the atom which extends beyond the shell. And so I think that a really nice, reasonable, rational way to start looking about this is the atom. What we have is something more like a spider web of atoms, actually. And there's some system of relay which is conveying all of this, but the details of that are probably beyond the scope of our conversation for today. A really unfortunate consequence of people not thinking about atoms that way at the time of what I would refer to as the death of the ether, right? When people stopped worrying about how light was transmitted, was that they assumed there were atoms and then there was the ether. So it was this kind of like Cheerios in a bowl of milk situation. And what they were doing is they were looking for, well, if all these atoms are sending the light back and forth here on Earth, then there should be a little bit of drift as the Earth moves around in its orbit. The unfortunate part of that analysis is that they're assuming that this ether stuff, in other words, that which is waving during light, the connectors of the atoms, that stuff is somehow separate from the atoms themselves. However, what I'm trying to suggest to you here is that, and what I think will become something revolutionary in the future, is that the atom's surface itself is an extended structure. So the atoms kind of carry that medium with them everywhere they go. And if you look at what Einstein wrote about the ether, he kind of described his general relativity as something of a non-kinematic ether, right? That it wasn't something you could put your finger on because, like, wherever you move your finger, the little pieces of it kind of correspondingly move along with it. So it's a very difficult medium in that sense to probe with atoms because it is in some sense the atoms itself. Yeah.
I don't know if this would be the right word to describe that. Would that be like omnipotent or?
In what way?
I guess like.
Omnipresent?
Yeah.
Yeah. I mean, it's a hypothesis, but I think that this kind of visual tool that I'm trying to give you right now, it fits with the data, right? So we're going to talk about some interesting pieces of this in a second, but for the longest time, even when I don't remember, it's been a long time since I took intro physics or intro chemistry, but you usually learn about light as kind of this thing that shot off from an atom, right? But the weird thing is, the weird piece that never makes it into that puzzle is that you never have light without two atoms. It's always got to be something to receive the signal, right? And this was kind of a contentious view. The first person to announce this, and I'll read you a quote by him later, was G.N. Lewis, who was one of the dons of chemistry. He gave us the pairing, bonding, the Lewis pairing of electrons and stuff you learn about in chemistry. But he kind of made this announcement at some point back in the 30s that, I think it's kind of ridiculous that when we talk about light, we don't talk about two atoms being involved. Because I think that what we're looking at is some sort of an equalization of energies between two atoms at all times. In other words, both atoms are playing a role. It's not just the flashlight, it's also the wall that's involved, the screen itself. Yes, and then yes.
Are there any other elements that also require two atoms?
I would say everything that we can observe, essentially. And I think that's why you see a lot of really quasi-mystical headlines in the physics space these days. You'll often hear like the observer is important in these quantum experiments, stuff like that, right? And I think there's some validity to that, definitely, because you can't remove the observation from the experiments because those atoms are networked in such a way. I really like the metaphor of network, like very much like a spider web. And there's tensions being applied that are corresponding to the two partners, at least two. And when we get into trying to explain weird stuff like that double slit experiment, like how does the photon go through both slits at once? It's like, well, it's not a simple bowling ball. These atoms are all connected to each other and they're all applying pressures at one another. And if they're the wrong phase of pressure based on the travel length, right, based on the geometry of the setup, you're going to have cancellation of that reception at wherever you're looking sometimes. It's all very geometric and easy to understand. And there's nothing spooky about it. But you can't think about the atoms as these little bowling balls that shoot these magical things off. You have to think the atom has some sort of extended structure. It's obvious from the radial distribution of the electron that the electron is not just in this little shell of the atom. It has some extended structure to it. So, yes.
So, okay, I'm glad we're going over light.
Yes.
It always confused me in AP chemistry. And, okay, so I know it has something to do with, like, electrons going into an excited state.
Yes, we'll
Like,
get there.
What makes them so excited? And when do they go back, like, where they were? Into
Yeah.
the original?
That's a great question. Let's just go there right now. I'm going to come back to this in a second. So this is probably what you're referring to. So this is essentially the Bohr model of the atom, right? The idea is that you have a nucleus at the center of this dot, right? And that the electron can get excited into energy level n equals 1, n equals 2, whatever, right? And then as it relaxes from its excited state, a photon is given off, right? Some energy, some light is given off. So what the heck do these things mean, actually? Like, what is an energy state? Well, this is a little confusing of a diagram, and it's unfortunate that this is still the one that we use in intro chemistry books today, because it kind of implies that the surface of the atom is actually physically expanding and contracting between these. That's not what it means at all. These energy states are actually like really poorly ill-defined, actually. But what we can say is that the surface of the atom is in some sort of constant freneticism. It's vibrating, for lack of a better word. Now, how it's vibrating is very, very poorly understood. Is it expanding and contracting? Is it twisting back and forth? It's doing some sort of oscillatory behavior that we approximate with this concept of energy level. It's really unfortunate because the math of quantum mechanics doesn't really allow us to say what it's doing, only that it's doing it more frenetically when it's at a higher energy state. What's interesting, though, is that as it vibrates into higher and higher energy states, these are actually the spherical harmonics of hydrogen. That's a big mouthful of a word, but what it essentially means is this. If you take, like, say, a string, like a guitar string, and you pluck it, right? It vibrates at some predictable wavelength. The string, you can literally see it going up and down, right? If you move your hand up, let's say, partially up the neck, you get some multiple. You get a higher frequency, so you get some multiple of that frequency. Another way to describe the multiple of that frequency is as a harmonic of it. Now, you can do the same thing with a beach ball. You can vibrate a beach ball such that it has harmonics to it. You can have second harmonics, third harmonics, and so on and so forth. What these energy levels actually show us in the chemistry modeling is that as the electron surface of the atom gets more and more energized, it changes shape, actually. So it takes on these new orbital shapes. You've probably heard them in chemistry as orbitals. These are important in bonding and stuff. So that's really interesting, that there's some oscillatory behavior of the surface of the atom, and as it jumps up into these new states, it changes shape, literally, and it changes its ability to bond in new, interesting ways. And then as it relaxes, it gives off light, right? It gives off some impulse of light, which can be then taken up by somebody else who might get excited into a new energy level and change shape as a result of it. I'll get to you in a second, Nolan, 1 second. Now, you can see this kind of thing. Have you guys ever seen these Chladni plates before? Pretty cool stuff. If you just take a microphone, put it on a plate, and throw some sand on there, and you have like a synth or something that you can adjust the tone, go into that, not a microphone, sorry, speaker. Put the speaker underneath the plate, and you adjust the tone going to the speaker. Different tones will excite different geometric patterns just based on the resonance of that surface. They'll excite the sand to fall into these predictable patterns. And what's really interesting is that as you tune the energy, the tone, right, a higher frequency tone to it, you put more energy into that tone, you go through these phases of chaos where it doesn't really seem to have any form to it at all. But then, bam, it snaps into a shape. And then you'll do it some more, change the tone a little bit more, and then it'll snap into a new shape. The atom's kind of like that too. It seems to have these very discrete shapes it takes on. And we call those shapes energy levels. So what's really interesting is you can put a little bit of energy, you can put some energy into an atom and nothing happens. You have to put an actual quantized unit of energy into it. And people realized at some point that, and I'll tell the story of that light is very much the same way. It's kind of an all or nothing situation. You can have certain amounts of energy that don't actually give you light. They have to be these units, which we call photons worth of light. Certain amounts of change of energy has to happen discretely. So the energy levels really just mean these positions that give us effective changes in the shape of the atom, effects like light itself. It's kind of bizarre, but you can kind of think of the atom as this kind of blob that's vibrating. Of course, it's not as simple as these shells, right? Like I said, it's furry. It extends into space much farther than its shells, its chemical shells. But it's really spooky stuff. Yes?
I guess back to like the two atom thing you were talking about.
Yep. Yeah, let's go there.
We're talking about wavelengths and whatnot. Would you say that the wavelengths are being caused by the atom's disturbance or excitement or whatever, or would you say that there's wavelengths either inside or impacting the atom? Like, is the atom acting for itself, or is it being acted by something else?
Yeah, I think that's a chicken or egg question. That's what's really interesting about it. So I'll just read you this quote, if I can even see it. This is G.N. Lewis. He wrote this in 1926, actually. This is a picture of one of my mentors. This is Carver Mead, who's a Caltech professor, who developed a lot of Lewis's ideas. But I'm going to read you the G.N. Lewis quote, which he says, "I'm going to make the contrary assumption that an atom never emits light except to another atom. I propose to eliminate the idea of mere emission of light and substitute the idea of transmission, or a process of exchange of energy between two definite atoms. Both atoms must play a coordinate and symmetrical part in the process of exchange."
I feel like there's a parallel with this, of like the thing of, if a tree falls down in the woods and no one's there to hear it, can it actually be heard? No, because the actual frequency of sound has to be observed by something that can actually inherit that wavelength. So if there's no actual organisms that can identify the sound, it theoretically doesn't make a sound.
Yeah, I mean, air molecules might be moving around and stuff, but it wouldn't be a sound, right? Because you need ears to have a sound, or a microphone or something. Basically, got to be a human or an animal or something. So this is actually a pretty revolutionary idea, and Carver's done an incredible amount of work developing the mathematics of this idea that essentially what's happening during light, and he doesn't have a nice rational mechanism for this, although I think one is hiding in plain sight, that there's two atoms involved in light. One of them is in one oscillatory state. Let's say it's in a higher energy state. It's vibrating faster. Vibrating how? Well, that's tricky to piece together, but it's vibrating. Another one is vibrating in a slightly lower state. This has become unstable. Now, the way that this really fast one relaxes into a more stable form is it has to push some of that freneticism onto its partner over here. And when it does that, there's a wave of light that occurs, essentially. And so atoms can do this back and forth forever. They'll essentially, especially if you have a really nice reflecting surface, like that's the way that lasers work, essentially, is you get a bunch of atoms just doing this back and forth between each other in a chamber, and then you focus it on something. And you get all consistent, same wavelengths of light. They're really nicely in phase with each other, right? Because they're all just pumping back and forth. Microwaves work very similarly. There's a lot of our technology that works on this principle. So what's just really bizarre is that this hasn't really made it into mainstream quantum physics, despite all of the work. There's another gentleman up at University of Washington in Seattle named John Kramer. I've had both these guys on my podcast. Carver's been on a couple times. He's a really brilliant guy. but the idea is light is this sort of equalizing process between these atoms. It's equalizing some sort of freneticism of the atoms themselves. And that's really, really important to know, because if we just continue to treat light like this little magical bullet thing that flies around, we might miss something really critical. And like I said, it might seem esoteric, but everything that we're going to talk about in astronomy can seem esoteric until you start realizing that the future of our power here on Earth depends on us understanding how the stars work. Now, next semester is all about how the stars work, and I'm going to go super deep into that because I think there are huge revolutions to be made in that, and I think they will feed back onto our technology here on Earth, which is going to be really exciting. But needless to say, if we don't understand light, we're not going to understand anything we're seeing in our telescopes because we'll be misled and misled and misled. And so this is all super important background for going into what we're going to be looking at as we go through the solar system. Questions before I cruise on? Because I'm gonna talk a little bit about stars next. Hopefully somebody's having their mind blown a little bit because you've thought about light as little bullets of magic for your whole life, and you're starting to think about it a little differently. Yes.
I guess here's another, I guess I would consider myself a conspiracy theorist for this.
Brilliant.
Like actual colors have wavelengths within them, and when you project those lights, it interferes with atoms in different ways.
Mhm.
So actual light impacts, like observable light impacts, physical surroundings. Is that a possibility at that point?
I mean, yeah, colors. I mean, color is sort of like tone, right? It's a perception thing. You can get color in lots of different ways. You can get it literally because the atoms are giving off that wavelength. You can also get it through interference, like the peacock, for instance. The peacock is not actually colored the way that it looks. The reason the peacock looks so brilliant and iridescent is because it has these tiny little ridges on its feathers, microscopic ridges that lead to constructive and destructive interference of the light in such a way that it amplifies certain colors. It's really a pseudo-coloring. And you see this a lot in the bug world in general, like beetle shells, scarabs. In general, there's a lot of colors that aren't really being given off by the atoms. They're just the results of interference. Yeah.
I think it's really cool that on that, a lot of bugs like butterflies, all the blue butterflies aren't actually blue.
Yeah.
There's only one that has true blue pigment in its wings.
And when we say pigment, we mean what the atoms are actually giving off, right? So
It actually is, but anything else, like that's why blue is such a weird color in nature because it's not real, kind of.
that's interesting, yeah.
Interference colors or like a mixture of colors, so it's technically not blue.
Yep. So there's interactions that are responsible for a lot of our perceptions. And I just, to that end, I want you guys to understand that light, when I say light, I literally mean the entire electromagnetic spectrum, right? I'm not just talking about this stuff, the colors we can see, right? Which turns out to be a really narrow band, actually. It's not an arbitrarily narrow band. And we'll talk about why that is the color that we see. There's a perfectly good explanation for it. But light covers everything there's tons of light in this room that you can't see with your eyeballs. There's Wi-Fi signals bouncing around at gigahertz frequencies. There's really tiny lights, cosmic ray lights that are just so high energy and really, really fast frequencies that you can't possibly see with your eyes, right? So we're tuned to this really narrow band with our eyeballs of the light that exists in the room with us today. Probably for the better because it would be absolutely blinding otherwise. So light is this huge spectrum, and generally speaking, like you can see, this tiny little narrow band is the visible light spectrum, right? It's a very small range of wavelengths that we actually see with our eyeballs. And of course, it spans from the longer red colors down to the shorter blue colors. Now, some animals can see a little bit better or a little bit worse, but a lot of bugs can see down into the ultraviolet range. And I don't know about infrared seeing. Maybe there's some animals that can see in the infrared. I don't know. Somebody can tell me about that later. Yeah.
So light, I really cannot wrap my head around light, and for some reason it just doesn't.
It's okay. Ask questions. Let's see if we can make some headway.
So, one of the, so I really get, like I said, the telescope stuff, I really just cannot wrap my head around it. So how can they take like telescopes and pictures that can see the like infrared and the things that we can, and then translate that into things that we can?
That's a really good question. And it really goes back to this. If you can wrap your head around this simple picture here, it'll get you a long ways. Because this is the same, a transmitter works the same way as a receiver for a radio image. But you have essentially a wire here, right? And all that's happening is that with some, in the time domain, so across some unit of time, the polarity of that wire, so which direction the electricity is flowing, changes with a characteristic time element, which corresponds to the light that's either being emitted or received, depending on whether it's powered, so whether you're driving it to oscillate like that, or whether it's just passively receiving electromagnetic radiation of some sort. And what you can do is you can build a sensor system that essentially has tons of little antennae all over the place. This is what's in your cell phone, essentially. You've got all these tiny little photo antennae that are capable of relaying that information about the wavelength, right, the time domain of the periodicity, because the frequency of that flip-flop results in the wave length that's characteristic. Remember, light travels at a constant speed. So if you know how often the wave is being made, you know how far it's gone, because it's traveling at a constant speed, and so therefore you know the wavelength, which means you know the color of it too. And so you can get information like that. And we basically we can build sensors that are essentially just as simple as this, that can give us information about light that we can't see with our eyeballs, because it's a longer wavelength than our little rods and cones are set up for in our eyeballs. Does it help?
I just don't think I can wrap my head around how that things that we can't perceive being put into a way that we can.
Well, you just need an antenna that has more, you need an antenna that is better than your eyeball, basically. That's all there is to it. So these antennae, I mean, they're not better, they're not more versatile, but they can perceive different time scales. They can pay attention to frequencies longer than what your brain is capable of doing. And that's really all it is. You basically have an antenna. So you have three of them. You have a few different colors, right, in your eyeball of these little antennae. They're chemical. In other words, when they receive a particular frequency of excitation, they change the shape of their molecule, which gives an impulse to nerves and tells you that there's some color in your eyeball. They're basically just a little antenna, though, but they're only really specific for visual wavelengths, right, which is a particular color. You don't have any rods or cones in your eyes that can respond to infrared or ultraviolet. You just don't have the right size antenna, basically. Yeah, keep going.
Does this tie into like, because I feel like I remember when I was younger, like the philosophical question where I was talking about the conspiracy theories about like people might have different colors that look different to different people.
Yeah,
or,
yeah.
Like, the whole thing where it's like maybe like when I know it's red, been taught red, and I like if I transport my brain to someone else, maybe they see something completely different. So
Yeah. Well, perception's a different problem altogether.
Yeah, so how does that argument tie into like, well, it just is a certain wavelength, so when we all perceive.
I mean, we may perceive, I mean, you and I may perceive the same wavelength such that we could call red red. Like, we wouldn't have to be colorblind, but I'll never know whether what I see as red is the same thing you see. Because there's a whole level inside of our brains. You know, I have several friends who are like colorblind of different sorts. And it's kind of impossible for me to imagine what that's like. And it doesn't even seem to bother them that much, actually, right? Because that's all they've ever known. And they can still distinguish, depending on the degree to which their photoreceptors are mutated, right? They can still perceive different shades, maybe, of red, but they look a lot like green to them, too. So the perception side of things is a real nightmare. I mean, you can go completely down the rabbit hole of that and arrive at the conclusion that you can never really know if something is conscious or not. Because the only thing that ever knows is the thing that's conscious, ultimately. You can say it looks conscious, but this is the problem with all these AI systems, is they're like, well, it has to be able to pass the Turing test. In other words, it has to be able to fool us into thinking it's conscious. But like, they did that like 5 years ago, you know? And people still don't think that the AIs are conscious, right? But how would you ever really know? Yeah, I don't think you can. Yeah, yeah. Yeah. Well, yeah, that's a tricky one to reason through. I mean, yeah, I have thoughts on that, but it's beyond the scope of this class. Yes, please.
So the electromagnetic spectrum, how you were saying, there's like radio waves and all this stuff that we can't see.
Yep, it's all light.
Where does radiation come
It's also light. It's another word. So we have all these words that get confused, right? Electromagnetic spectrum, light, radio waves, gamma rays, X-rays. When we say radiation, like colloquially, like in just kind of slang, like news speak, whatever, people generally mean light that's harmful to your DNA. So what happens, and this is really interesting too, why in the world would light be harmful to your DNA? Anybody? Well, I mean, if you yes,
Mess with the atoms.
yeah. Why though? Like, it's
Yes, with the light excite the atoms or make them go wild.
yeah, it makes them go wild. I mean, it's not too hard. Like, your DNA is a very delicate structure. Actually, it's really easy to screw it up. And yeah, if you have light that has too much energy, so you have some atoms, let's say that you generate in nuclear reactions often. Like a lot of these X-ray machines involve some radioactive element that's essentially making light at a really high frequency. And those atoms are excited at a really high frequency. They're going to dissipate into whatever they can get to, right? So they're generally shielded in these inert lead molecules that will sop up all of that loose energy and not relay it through so it can hurt you. And then they open the little lead door at some point, and all of a sudden those atoms in that chamber, they're going to resonate with whoever they can, right? And so generally speaking, that's a bad situation if you get too much of it, because your cells are made out of atoms. Your atoms are very, open to being excited, and you can just shake your DNA apart, basically. And if your DNA gets shaken apart, it's a real catastrophe. Yeah.
I get how physical sunscreens work because it's basically like putting mud on your face or like to block.
It's more like the lead door, kind of, yeah.
Yeah, but how do chemical sunscreens work to absorb UV light or to protect it from like?
Oh, it's kind of like the lead door still, right? You have basically these molecules that act like antennae that are, soluble, so you can slather them on yourself. Like zinc is a really obvious one. There's more complicated ones, but they will basically act like little antennae that absorb that frequency of light, like the UV that we consider dangerous. By the way, why is UV light considered dangerous and not, I don't know, red light or something like that? It is higher energy, but I think there's more to it than that. Yeah. It is, yes. So it is higher energy, but it's not really high energy. Like, it's not like an X-ray or like a gamma ray or something, but it still will destroy your DNA.
Well, is it more common in our everyday lives? Because, I mean, I'm sure the sun kind of transmits more wavelengths of light than just UV.
Yes, we're going to talk about that for sure. We'll make it there today.
It's like more easily able to get in through the atmosphere and like
Actually, no.
more common in our...
Yeah, that's a good hypothesis, but it's not true, unfortunately. So there's less UV light actually coming from the sun than visible light, or different red lights. There's actually not a really nice answer for this one, but I think what it has to do with is there being some vibratory overlap between the molecules in your DNA and the actual wavelength of that light. So in other words, you guys have maybe seen this before. Anybody play music, play guitar? Nice, awesome. You go to a guitar store, right? Have you guys ever had this happen when you start playing a guitar and then all of a sudden the one on the wall starts vibrating too, right? When at a more basic level, an acoustic guitar, the sound doesn't come from the strings. It actually comes from the body of the guitar. And so the way that works is that the body of the guitar is shaped in such a way that it has this nice geometric relationship with the strings. So when the strings vibrate, it sympathetically vibrates the guitar. I think there's probably something going on with that with respect to UV radiation and the DNA molecule itself, which has a sympathetic vibratory nature. But anyways, I'm kind of in the speculation territory. Yeah. Yeah, let's do it. Can't hurt me.
I don't know, my special interest on it was like the Chernobyl crisis of everything.
Mhm.
So is that kind of what was happening if X radiation like noticing the delicate molecule?
Yeah, I mean, those kind of radiations, like you were asking about radiation, like when people generally speak about radiation in just like street language, they're talking about really high energy light. So X-rays, gamma rays, stuff way down there, right? UV is weird though, because it's actually quite close to visible light. It's not particularly high energy, and it is kind of all over the place. So there's something special going on with that one, and I haven't heard a really good theory for it. Yes, and
Well,
we'll
that's
go to
the
you.
doors that you were talking about. Respects with radiation.
Mhm.
People, I've seen articles about like people saying that like humans are being slowly affected by the radiation from like, our phones and
Mm.
and stuff. Would that lead door kind of be in all of our technology in a sense to protect us from radiation?
Unfortunately not. Well, I don't know. So I've tried to go down that rabbit hole many times. There's a lot of contradictory literature about that kind of level of radiation. So the good news is this stuff is the most dangerous, right? It's really high frequency radiation. The radio waves in your phone and stuff and the 5G networks that we use for Wi-Fi right now that I'm using for this presentation, they're all the way down here. So they're way, way lower energy, first of all. So that's good. I would also suspect that this really long wavelength, by the way, these waves down here that are part of your like cell phone radiation and stuff, they're huge. They're like the length of this classroom. They're enormously long waves. They generally, I think that's why they can be relayed through walls so nicely, is they use the entire wall as a resonator, and they can retransmit. So you get this. It's very good at penetrating through thin structures and stuff like that. But in terms of its like health consequences on humans, it's very hard to see. Some people have done these experiments where they'll like put these radio emitters, like cell phones, like right next to like cell culture dishes, and they'll demonstrate different malfunctions of the cells. But in terms of human beings, it's very tricky. I've seen some kind of convincing studies about the side in which people use their cell phone and brain tumors as a result, like that some correlation there. Very hard to like say whether a correlation is a causation. Maybe there's other things going on. Yeah, what do you got?
I'll make it quick, but I always heard guys who always worked at like nuclear facilities, like in North Dakota, where they store some like nuke bombs. They'd always come back, and I don't know if it was true or not, but they'd always tell me like everyone who had like a child near the base or like worked on the base would always have like girls.
Weird. That's
Yeah,
really, really weird.
I can't tell you if it was true, but I
Yeah.
heard it from so many people who came.
Yeah, I mean, there's definitely some gnarly contamination stuff going on that happens, and I've seen documented cases of that. It's really bad. I mean, it's not just nuclear stuff. It's a lot of industrial waste in general. The DNA is a delicate molecule. That's true. Yeah.
I know this kind of like, so you're talking about how the radio waves are like so long, so they can kind of resonate through things. Is that way, like, you don't get like sunlight through walls to like affect us and stuff?
I think so. I think so. I mean, I think you've got to really start thinking, all right, so I can see you right now, right? So light from these things, these fluorescent apparatus, is bouncing off your face and it's reflecting onto my eyeballs right now. But there's a lot of atoms in between us right now. I don't know if you noticed, but there's air in the room right now. Thank God. Right? So what's up with that? So it seems like light does certain molecules, particularly nitrogen, and most of the air is nitrogen. Like 80% of the air in here is nitrogen. Oxygen too, to a certain extent. It seems to be able to like the way that the way you'll find it written in your textbook is that light passes through it. I think again they're treating light too much like this magical bullet thing that just flies around in the world. I think the reality of the situation is you got to start thinking in terms of networks, right? Those atoms in between me and you right now are just taking all of the momentum of that signal that's coming from the light, and they're just passing it right forward to the next atom in front of them, right all the way down the line until it hits my eyeballs. So I think you got to really start thinking in terms of relay networks to try to understand this, especially once we get, and we're not going to do it in this class, but if we got into the weeds about interference and like the double slit experiment and some of these really spooky quantum things, you really got to start thinking in terms of relay of what's going on. Because what's being relayed at the end of the day, it's ultimately the electric polarity of that atom. And we have to we'd get completely in the weeds if we tried to come up with hypotheses for what the atom is actually doing during electric charge. But its surface is doing something. And when it's in the opposite state, when it's positive versus negative, it's doing the opposite thing. And so what happens is you can get cancellation if you have these opposite pressures at the exact same moment. And light seems to be the way that atoms relay that oscillation to one another across space. So yeah, I know it's tricky. I know this is pretty heavy, and we could probably do an entire course on light if we wanted to, and I would love to teach it, but that's unfortunately not the extent of what we have to get done here. Yeah.
I guess I just had a quick question, like what material absorbs light the best?
Depends what kind of light. It's very tricky. It's very tricky. Black stuff. So maybe this is a good segue into talking about this stuff, blackbody radiation, because this is one kind of really interesting kind of light. So if you heat up anything that is solid or liquid, and then you take a prism or spray a water hose in front of it or whatever you want, you need to split the light up, right? You will get this beautiful rainbow of colors, right? The way that all of these initial, people realized this back in the 1800s, essentially. They realized that when something was glowing, like an iron, the blacksmiths back then would be like working with these really hot furnaces. And I'm sure somebody just happened to have a prism or whatever, they had an eyeglass or something, and they noticed that it was making a rainbow, right? What happens is you can really optimize that situation by taking whatever's hot and putting it in a black chamber. And what happens is eventually the black chamber comes to the same temperature as whatever hot thing is inside of it. And that black chamber, and they made these by covering them in soot, so carbonized soot. What happens is that the light that's given off from that soot can be described with an equation where the peak color that you get off of that will actually tell you the temperature of that black body. This is called it's really just called blackbody radiation, and it's the core of star science. And it's absolutely critical that you understand this, because if you know what the color of the star is that you're looking at, the theory goes that you know the temperature of that star all of a sudden. So this was a crazy revelation. There's a huge problem with it, though. Yes? Which piece? Okay. This is actually called Wien's displacement equation. The B is a constant. It's actually called Wien's displacement constant. But the critical thing is that temperature and the temperature and the max wavelength are always proportional to some constant for a black body, of a given character. So you might make a black body chamber that's more or less black. Ideally, it would be perfectly black. But since all the chambers are slightly different, you end up with a different constant. Yes?
Is this really why water fire is blue?
Yes, exactly. Exactly. So it will move that peak, right? And you'll get a different temperature for it. So blue stars are thought to be really, really hot. Now, I'm going to tell you, that would be beautiful if it was true, but I'm not sure it's true. And we'll pick that apart in a second. Yes, please.
I'm not spectrometry is really going to temperature. Does this have to do with
Yes.
that?
Oh, yeah, we'll get there in a second. Yes, Shane.
I was gonna ask, wouldn't that, we're about to talk about it, but wouldn't it not make sense of looking at it to see what color it is to know how hot it is? Because the center, because isn't it, our stars are mostly gas.
We're just talking about the surface. Well, what you just said is the real problem, actually. What you just said is the real problem. So this is what heated solids and liquids do. Gases, when they're heated, do something totally different. And that's where things start to get really exciting, actually. If you heat up a gas, what you get is individual frequencies. You get little lines, actually. You get one color, and maybe you get a few colors from a gas, but you don't get a rainbow of colors. You don't get every single frequency in between with a nice peak, right? So, look, continuous spectrum for solids and liquids, lines of individual frequencies. Now, you might say, why in the world is that? I think there's a perfectly rational way to explain why that is. So if I have a gas, it's basically, we can approximate it like we've been doing as an atom, right? It's an atom. It can vibrate in a few different ways. Maybe it can go like this and like this. It has basically a few defined vibratory modes to it because it's a really simple object. It's one of the most simple 3D objects we can imagine, a sphere, right? So it would make sense that a sphere could only vibrate in a few different ways, right? However, when you start sticking those spheres to each other, now all of a sudden, not only can each one vibrate at its characteristic frequencies, but you have this vibration of the two of them whose electrons, whose shells have essentially merged, right? There's actually merged shells in all of these objects that are solid and liquid. Liquids are a little bit more transient, but we can still think of them as sharing electron. We'll say sharing actual surfaces of the atoms, right? So you have new modes of vibration that are possible. So it makes perfect sense that solids and liquids would have every conceivable frequency, some of them more than others, depending on how hot it is, but gases only do this. Now, this is really, really critical, and it's something worth pondering because it really matters for how we understand fusion technology. This is where things start to get a little spooky. So you're absolutely right that people have historically treated stars as gaseous objects. Now, that was a reasonable hypothesis at some point in time because they needed a way to explain how stars powered themselves. And there was a gentleman named Arthur Eddington who actually decided, and he made a very convincing mathematical proof that if he used the ideal gas laws and applied them to the stars, he could find a place where there was so much gas that if you squeezed the gas together under the right conditions, you would actually fuse the atoms together, make new atoms, and it would release some energy. And that this power would be sufficient to generate the energy that we see from stars. So the state equations for the stars were constructed using the ideal gas laws, and it stuck. And there's a huge, huge, long history in the 1800s about arguing about what the stars were actually made out of. And we don't have time for that in this class. But nowadays, if you actually go and talk to an astrophysicist, a solar physicist, and you say, well, how in the heck is the star made out of gas if it has this continuous spectrum like we only see from solids and liquids? They'll say, well, it's not exactly a gas, it's a plasma. Plasma is the fourth state of matter, it's completely misunderstood, and so on and so forth. Well, that's problematic too, because we can make plasmas on Earth all the time. In fact, there's some in these light bulbs above our heads right now. And I guarantee if you whip out a prism right now, you're going to see nice, beautiful lines coming from those plasmas above your eyes. So I'm not sure that it really lets them off the hook exactly to say, to still use the ideal gas equations to describe how fusion works in the stars, but at the same time recognize quite patently that gases never, ever give you a continuous spectrum. So there's some sort of serious confusion going on about the actual state of the matter in the stars. Now you might think, it doesn't really matter that much. It matters a lot, and it matters not only in terms of the fusion technology, which I'm going to run out of time, but I'm happy to unpack that for you guys next time if you remind me. It also matters because the temperature that you're seeing, that you think is a temperature from a blackbody spectrum, it might not just have to do with the temperature of the star. You had a question, sorry.
So continuous spectrum is what we get from stars, right?
Yeah.
And bright line spectrum is from gases.
Yes.
Is that all gases? Because when I looked about this, I feel like we only focused on halogens.
Yeah, it's all gases. Yeah.
Then how do we get the continuous dark lines?
So I didn't have time to go through these Kirchhoff's laws with you guys, and I think it'd be wise for me to start there. I think we'll start here with this slide because there's too much going on here for us to just rush through it. We'll get to that, but basically gases will also absorb light at whatever frequency they emit light at. So if you stick a gas in front of something like a sun, now the sun does have a gaseous atmosphere that's quite obvious. It's called the corona, and it has lines of absorption in the corona. So pieces of that rainbow are blotted out by little lines, right, from the gases that are in the corona. So there is a gaseous component to the atmosphere of the sun, which is called the corona. But the body itself in terms of trying to argue that the body itself is anything like gaseous is a real problem. I remember the example that I was on my way to explain to you guys, and this is what I'll leave you with. If I take a bunch of carbon, let's say I have a star that's made out of carbon. Well, whether or not that's even possible is a different matter, but some say it is. But anyways, let's say that we have a star made out of carbon. Okay, it's really hot, right? It's black, because, right, it's made out of soot, basically, right? So we can read the temperature of it using the Blackbody equation, right? Great, so we know the temperature of the star. What if I have a different star also made out of carbon, except instead of being soot, it's made out of diamonds. Diamonds are also pure carbon. And I heat up that thing. What happens now? The light's going to be able to pass right through it. It's a transparent substance. So the optical properties of a material do not just depend upon the temperature of the light. They also depend on the arrangement of the atoms. The only difference between soot and a diamond is that in soot, you have this nice hexagonal arrangement of the atoms. You have a carbon at every point. The diamond is a little bit trickier. It's actually more like these cubes that are kind of overlaid on one another. I don't know how to draw it for you in 3D right now. It's a different arrangement of the carbons. They're in a different crystal structure. And the result of it is that light stops right at a black body, right? No light penetrates through something that's black, at least visible light. But light goes right through a diamond. So the way that the atoms are arranged makes a huge difference on what's happening. And that's going to prove to be really important in terms of interpreting some of this weird stuff that we see in the sky. Last question.
Yeah, so could that relate with like diamond lenses and whatnot and how to interpret certain lights through that?
It more relates to when we see something that we think is really heavy but really small in the sky. Because it turns out, and we're going to get to this, so much of this is broken into next semester, but it turns out that when you look up at a star in the sky, you can't actually tell how wide it is. You can only tell how bright it is. And the question becomes, if it has a lot of gravity and it's not very bright, is it some ultra-dense new form of matter, or is it just a different lattice arrangement of the atoms in that substance? Yes?
So as you were saying, we were measuring the temperature of the stars based on the continuous spectrum.
Yes.
Is that accurate?
Yes.
We're applying that to, okay.
Well, no, sorry. It is accurate that they have a continuous spectrum. Whether it's actually the temperature of those objects gets into really tricky territory.
Because especially if we've already determined that it's gaseous, but we're applying different rules to it, so that's kind of like, so what is it, and also, what is the arbitrary measurement then, and why would that, so is that the arguments, why would that make sense if we're not applying, all of these pieces are not puzzling at all. There's 5 different puzzles and we're trying to make one picture.
If you want to see an astrophysicist lose her cool about this on my podcast, check out the episode with Valentina Zharkova. She's one of the world's premier solar physicists, and she absolutely flipped out and walked out of the podcast. It was really fascinating. It's a huge problem, actually. It's going to revolutionize things in the future. I'm absolutely certain of it. Yes?
I have another cue. So is there a chance the bright line spectrum could be pieced out like that because the atoms are physically further away? Because between gas and liquids and solids, they're spaced out more?
It's supposed to be really dense, is the problem. Here, I'll let everybody else go. Come up here. We'll talk about it some more. Yeah.
Dense gas,
A liquid?
right?
Yes.